Last class we discussed about the force experienced by a magnetic force experienced by a current carrying conductor. Uh, Today we will discuss about Fleming's left hand rule. So I think already you know the what is Fleming's left hand rule. So I'll write down this one. So first what you have to do, you have to stretch the left hand, stretch the left hand such a way, such that the forefinger the central finger and the thumb are mutually perpendicular to each other. So when forefinger points in the direction of magnetic field and central finger points in the direction of current, then the thumb gives the direction of the force acting on the conductor. So this is the law that is called the Fleming's left hand rule. So now I will show with my left hand. This is the left hand, you can see. So this is your thumb and this is your central finger. This one is central finger. Okay, and then this is the forefinger. Okay, so like if you have to stretch in this way. So this finger, this finger will show the direction of the magnetic field. This finger will show the direction of the current, and the thumb will show the direction of the force, okay, experienced by the current carrying conductor. So you understand, stretch the left hand such that you have to use the left hand, don't use the right hand. Right hand rule is different. Such the forefinger, the central finger and the thumbs are much mutually perpendicular to each other. When forefinger points the direction of the magnetic field and central finger points the direction of the current, then the thumb gives the direction of the force acting on the conductor. Okay, so this is the law. You can say this is the Fleming's left hand rule. So now next one we'll go to another thing. That one is the charge particle moving in a uniform electric field. So I'll just explain this one. Just a minute. So first write the heading: charge particle moves or moving unit, moving in a uniform electric field. This is the thing we are going to learn today. So for that you have to draw one diagram. So take two plates. So this is the plate, this is one plate, and this one is another plate. Okay. So now this is the plus charge. Here the plus charges are there. Plus charges. And on the other side there is minus charges. So minus charges will be here. Okay. Now already we know that the electric field will start from plus and will go to minus. So like this electric field will move plus to minus. Like this. And here one axis is there. So this is your y-axis and this is the x-axis. X and y. Now electric field, this is electric field E is applied, and these are the charged plate. And here is also the charged plate. Now in this side there is one detector, or you can say screen. The screen is there here. This side there is a screen. Draw a screen here, like this. Like this, a screen will be there. Okay, screen. Now what will happen? Suppose a charge plus Q, this is a charge plus Q, is moving in this direction with velocity v vector. Okay. Then when the force will start to apply in this direction from plus to minus, so what will happen? The charge particle will start to bend in this way. In this way, it will start to bend. Like this, it will go and bend along with this one. So it will bend in this way. And after bending, why it is bending? Because the magnetic electric force is applying on the charge particle. And after bending, that it will go straight here. This is a straight line. This one is a straight line path. Why? Because there is no electric field is applying, so it will go straight line. So until unless suppose that if there is no electric field, then what will happen? The charge particle will go straight and hit the screen in this point. But as we placed one electric field, the charge particle will bend in this direction up to this. Then after that, the charge particle will go straight. After this one, will straight. So this is the point the charge particle will hit the screen. Now you have to find out that whether this path or the type of paths is this is a circular path or what is the things that we will learn today. So now question is that how much force is applied on this charge particle. So let m is the mass of the charge particle. So how much force is applying? So F is equal to, already we know, F vector is equal to Q into E. So what is acceleration? Acceleration on the charged particle in this direction, in the y direction. Acceleration is a vector is equal to force by area. So that means F vector by m. So F means QE. So QE by m. So this is the force. Sorry, acceleration. Okay. So A is equal to this. Now we'll only discuss with the we'll only deal with the magnitude of the A. So magnitude of A will be how much? QE by m. So this is the magnitude of acceleration. Okay, now see here two things happens. One is the charge particle is also going towards y direction. So this is the y direction. You can take this as a y length, y length. Okay, you can give the name also. This is O, and this one you can say this is O dash. This point is O dash, and from this x axis the distance is y, and from here to here the distance is x. You see from x. So you can say this is the horizontal distance traveled and this is the vertical distance traveled. So we'll discuss about the two distance travels here. So first we'll discuss about the horizontal motion. So write the headings for horizontal motion. For what will happen? Suppose the S is the distance travel. S is equal to for horizontal. You don't think about the vertical now. Only you think about horizontal. So S is equal to x, because horizontally distance travel is x. Now what is the velocity in the horizontal direction? That is uh, u is equal to what? U is equal to, you can say, v. Okay. And is there any acceleration in the x direction? So there is no acceleration. So a is equal to 0. Okay. So that is the thing we can get from the horizontal. Now we'll use the formula S is equal to ut plus half a square. S is equal to ut plus half a t square. So what do you get from here? So what is x? S is equal to x. So x is equal to u means what? U means v. T is there, time. So remember, the object will take the same time when you go from here to here. Also the object will take the same time from from here to here. Okay, so that is why the f is equal to vt and rest of the things are 0. So you can get t from here. T is equal to x by v. So that is the t you get from the equation, from the horizontal motion. And we will now discuss about the vertical motion. For vertical motion, so s is equal to what? S is equal to y. Okay. And then u is equal to 0, because see there is no vertical velocity. U is equal to 0, and a is equal to, in the vertical direction the acceleration is there, and that is qv by m. Okay, so now I'll put the, again we'll use the same equation. S is equal to ut plus half a t square. So you can write y is equal to, this is 0, this part is 0, so half a is acceleration, so you can write qe by m. And in case of t, I told you the same time it will take to go from here to here, or from origin to this side. So t is, you put the value, t is equal to x by u whole square. So that means half qe by m, u will come this side, u square will be there, u square into x square. So see this part, half q e m, this is all constant. This part is completely constant. Okay, so you can write this is constant, right? K is equal to, k is a constant, k is equal to q e by 2mv square, okay, is equal to constant. So now we'll write y is equal to k into x square, okay, k into x square. So you know that the equation of the parabola is y is equal to 4x square. This is the equation of the parabola. So you can learn from this equation, we combine this x-axis and y-axis motion of the charged particle moving in the electric field. So what will happen? The charged particle moving in the uniform electric field follows the parabolic path. So you can write that a charged particle moving in a uniform electric field follows parabolic path. This parabolic path. Okay. What is the parabolic path? O dash. O dash. Okay. So today is up to this only. So next class will continue the charged particle moving in a uniform magnetic field. Okay. So thank you very much.